All right, looks like we are at the top of the hour. Just as a reminder, everybody's line is muted. At the end, if you have any questions, feel free to raise the hand in there, or you can type in a question, and I'll try to unmute your line. Other than that, we're excited to have everyone join this next installment of the Central Plains Sioux Community R2O webinar series. Today we have the pleasure of Dr. Jana Houser from Ohio University. For those who don't know, she has an extensive background in observational analysis of tornadoes and supercells using rapid scan mobile radar observations. So I was blessed with the opportunity to see some of this work from her at the AMS annual meeting this past January down in Austin. And Jen has graciously accepted our offer to partake in this R2O series today, and will be presenting to us on none other than the rapid scan mobile radar observations of tornadogenesis, and specifically some fascinating findings that further support ground-up tornadogenesis in supercells. So that's all I have. With that, the floor is all yours, Jana.
All right, great. Well, thank you so much, Aaron, for the opportunity to deliver this webinar. I've been really excited about working with operational meteorologists and communicating some of what we've found on the research plane and translating that to operations. So thanks. Without further ado, I think I'll just proceed. I want to first acknowledge some contributors to this work. As with any great science, I have not been alone in my pursuits of the truth, so to speak. Dr. Mike French, who was a colleague of mine as a grad student back at Oklahoma, he contributed some information to this, and I heavily referenced some of his findings from his PhD dissertation. Anton Simon also contributed with some work that we did together on the El Reno 2013 tornado. Dr. Jeff Snyder is a collaborator from OU as well. Skip Talbot, John Allen, and then my PhD advisor, Howie Bluestein, also contributed predominantly resources. So I wanted to start here with kind of a recap and what probably might be a little bit of more kind of classroom type learning here, but since it's probably been a little while since many of you have attended a mesoscale class, I thought it would be a good idea to sort of review the traditional hypotheses that address how tornadoes form to begin with. So historically, there are two predominant hypotheses that are used to explain tornado formation, but these two hypotheses essentially are conflicting regarding the actual evolution of the rotation that's associated with the tornado vortex. So the two traditional hypotheses are the top-down hypothesis and the bottom-up hypothesis. So in a sort of conventional sense, the top-down hypothesis, also sometimes referred to as the dynamic pipe effect, has traditionally been attributed to tornadoes that form from supercells, whereby the bottom-up process is more typically associated with non-supercell land spouch type tornadogenesis. So let's talk about these particular processes and some of the science and dynamics that actually goes into why these processes might theoretically be occurring in the atmosphere. So the top-down process, or the dynamic pipe effect, has its origins in some of the work that was done by Lance Leslie through numerical simulations and laboratory models of tornado vortices, and then was operationally supported by observations in the mid-1970s with the advent of the National Weather Service Doppler radars there. So what happens with this is initially when you have strengthening mid-level rotation, that rotation is going to induce a low pressure perturbation as a result of purely the dynamic effect between pressure and rotation. And this occurs roughly 1 to 3 kilometers above ground level or so. And with that low pressure perturbation, you have air that's drawn down from above as well as up from below, associated with a vertical pressure gradient force. So this vertical motion is then going to be accompanied by convergence that's essentially drawing the air into the upward motion and into the low pressure perturbation. So presuming that angular momentum is conserved, when you have convergence, if you have an ambient state where you have rotation, that conservation of angular momentum is going to imply that as air is converging, it's going to also increase in its rotational capacity. So this essentially happens until the point at which you achieve a cyclostrophic balance where the outward directed pressure gradient force is equal and opposite to, the inward directed pressure gradient force is equal and opposite to an outward directed centrifugal force. So once that balance is achieved, then air is drawn up from below and converges and so forth until it too becomes cyclotrophically balanced. And basically you have this sort of series of progressing low pressure perturbations, actually both above and below your mid-level rotation, but we're generally predominantly interested most in what's happening below that low pressure perturbation. And it essentially causes the tornado vortex to build at progressively lower and lower elevations, almost in a discrete type manner, until it hits the surface, and at which time you develop a pretty concentric updraft and you get stretching and the vortex intensifies and you have a tornado. So observationally, as well as numerically, this process tends to be observed on the order of about 5 to 10 minutes. So from a perspective of a forecaster, you almost sort of hope that this process is happening, because when you start to see evidence of that strengthening mid to lower level rotation, that might be an indication that this process would occur, and you have maybe a lead time of 10 minutes or so to issue a tornado warning based upon the strengthening of that mid-level or low-level mesocyclone there. The alternative theory, this bottom-up process, happens when you have rotation that pre-exists that's already vertically oriented. So you already have vertical vorticity, and what happens is an updraft essentially moves over top that area of pre-existing rotation that can form by any number of ways. And when that updraft encounters that vorticity, it stretches it, and like the classic ice skater effect, pulls it in, converges, and intensifies that rotation, again, via the conservation of angular momentum. That's going to then cause the tornado to occur. This process, it's thought, will occur more rapidly, on the order of maybe a minute or less. And again, oftentimes this is attributed to the tornadogenesis process with landspouts, as well as perhaps some squall line type scenarios. So Jeff Trapp and some co-authors in 1999 did a nice little study where they looked at 52 tornadoes from the perspective of WSR 88D observations, and they determined that about 67% of the tornadoes that occurred with supercells formed from what they described was a top-down process, basically where they incrementally saw rotation increasing, starting at elevations above the surface and then kind of incrementally occurring at lower and lower elevations. So some motivation behind my work here, as well as some of my colleagues, is that the traditional 88D radar network has a volume scan time on the order of about 4.5 minutes, 4 to 5, depending on what volume coverage pattern is operating. So traditional mobile radars, on the other hand, will have an improvement to that, and they have volume scans on the order of about 2 minutes, particularly usually for sector volume. So you're only scanning between a few, maybe a 90-degree azimuthal sector, but you're scanning at multiple elevation angles. So in the late 2000s, roughly 2008-ish, rapid scan mobile radars are developed. And there are a couple of these out there. The Dow 5 was perhaps the first pioneering rapid scan radar that was built by Josh Werman at CSWR. They had very minimal success. This particular radar tended to be pretty glitchy, and they don't really have very good case studies from the data that were collected by this. Another one developed by the Naval Postgraduate School is this MWR-05XP shown here. That was operated by Howie and myself and some other graduate students in the late 2000s. And this is a phased array, an actual phased array, and you can acquire sector volumes on the order of 10 to 20 seconds. So in comparison to even the 2 minutes of a traditional radar, you can imagine that we're seeing much higher temporal resolution on processes that are occurring with rapid evolutions, such as tornadoes, like we're interested in. And then the RAXPOL radar was developed at the University of Oklahoma, and that can acquire 360-degree full volume scans on time scales on the order of about 20 to 40 seconds, depending on how many elevation angles are contributing to that volume. So I'm going to be particularly focusing on data sets that were collected by the MWR as well as the RAXPOL here. And there are other rapid scan radars that have been developed since then. So some additional motivation here. If you look at this series of images over here on the right-hand side, you'll go from a kind of raggedy-looking wall cloud with some intervening precipitation, maybe a little bit of debris can be perhaps seen at the ground. This is the genesis phase of the EF5 tornado that happened in El Reno, Oklahoma in 2011. And then if you kind of go through this series of progression, notice 205116, both of these screen grabs were from that time. This one does not have a condensation funnel. This one does. So obviously very, very rapid process is happening here. 2 seconds later, you have an even more well-defined funnel. And then by roughly 4 minutes and 10 seconds between the initial photograph here and this final one, you can see that we have a very well-organized wedge tornado on the ground. So obviously there's probably a little bit of a time issue from the standpoint of the data being collected by the WSR 88Ds, if you're having essentially the entire genesis and intensification process occurring within the context of one volume scan, you can imagine that there's a lot of missing data in these 88Ds. So basically the scientific question involved here is, can we confirm or refute the top-down tornadogenesis process by using high temporal resolution radar data? So here I have a little image, a RAXPOL image of the 2013 El Reno tornado, and if you know, just for a little bit of eye candy here, we actually have a satellite tornado that moves in off of the periphery from the north and then kind of wraps around, and you have a little Fujiwara effect here where the parent tornado actually regresses a little bit toward that satellite tornado. So just a little fun image to check out there. So the predominant methodology that is used for most of these studies that I'm going to discuss here is essentially analyzing rotation by looking at the inbound and outbound radial velocity data through these mobile radar observations here. So we're looking at a parameter that I refer to as delta V, which is merely a difference between the maximum outbound velocity and the maximum inbound velocity, and using that as a proxy for the intensity of rotation here. So I identify what I define a tornado signature when there is a velocity couplet with maximum inbound outbound velocities of greater than 40 meters per second at a distance of less than 1 kilometer, or when there is a delta V greater than 40 meters per second within roughly 3 azimuth angles of each other. So this is going to allow essentially me to also confirm a tornado signature when you have a really wide, broad tornado. And then I track the rotation with time and with height here over the various different radar elevation angles. So setting the stage for this work, I'm going to here refer to Mike French's PhD study here. He wrote up a really nice paper in a monthly weather review entitled Re-examining the Vertical Development of Tornadic Vortex Signatures in Supercells. And basically he examined cases, 3 particular cases, using the MWR radars. So Ellis County, Kansas from 2008, Goshen County, Wyoming, which is the kind of golden tornadogenesis case from the Vortex 2 field project, and then this 2011 El Reno tornado, so kind of El Reno 1. I also investigate this tornado using RAXPOL data, and I'll talk about that here subsequently. So in his study, Mike basically concluded that 2 of the 3 cases that he investigated had pretty clear bottom-up evolution of a TVS. So by the way, a quick discrimination between TS versus TVS. So the MWR has a wider beam width, and therefore it's not able to fully resolve the entire tornado, so we refer to that as a tornado vortex signature. The RAXPOL has a finer beam width, and we are close to the tornadoes and are actually able to resolve the full tornado, so I refer to that as a tornado signature or a TS. So if you're wondering about that terminology, that's what's going on there. Anyway, so Mike observed that essentially none of these cases had a descending TVS pattern. But what he did observe was that there were these transient TVS spin-ups at various different heights that didn't end up being associated with the final tornado, but when taken out of context temporally with each other, and he actually like degraded the resolution of his radar data and kind of mimicked the scanning rate of an 88D, and he determined that within the context of this temporally degraded data, there actually was a descending TVS pattern. So kind of interesting here, what's happening is we're getting these sort of transient spin-ups at these various different heights that when we're not able to fully, recreate the temporal picture, we try to connect the dots, and our brain tells us that they're associated with one tornado, and you have this top-down scenario when you actually don't. So this image here just shows the time height evolution of the lowest 3 elevation angles for the Ellis County, Kansas tornado. And what you can basically get from this image is that there's a mutual intensification of the delta V couplet over time across these different heights. So you have differences in magnitudes, but they're all increasing essentially simultaneously. There's not a lag really between any of these different elevation angles here. So I later investigated this 24 May 2011 El Reno tornado using the Raxpol data. It was a closer data set. The Raxpol was situated closer to the tornado location. We had higher spatial resolution. Temporal resolution was comparable, but we had higher spatial resolution. And what I ended up finding was essentially prior to tornadogenesis time, which was about 2051, there was relatively weak rotation present almost ubiquitously across the board, but that rotation essentially simultaneously intensified over a roughly 2 volume scan time frame, which equates to about 30 seconds. I also noticed that about 4 minutes prior to the development of our tornado, we had this sort of brief spin up aloft where we had an intensification of rotation aloft. Now, if you were not having all of this data in between here, you could probably see how if you saw this initially and then saw this later, you would suspect that this is actually a top-down process here. However, with the addition of the extratemporal data there, we see that this was a brief sort of transient spin-up that weakened and decayed, and then later a tornado formed much more rapidly. This is just another way of looking at those data from a perspective of what I refer to as pseudovorticity, basically just a measure of the intensity of rotation divided by the distance that you're looking at that rotation. So what you end up seeing here is you have an intensification of rotation initially at low levels that kind of weakens a little bit, and you have this little blob that sort of appears aloft a little bit later, and then essentially within, from this volume scan to this volume scan, which by the way is on the order of about 20 seconds, you go from really not having a tornado to all of a sudden having a tornado. And again, that process was sort of started with this little blip there, and then, it's a little bit tricky to sort of extrapolate what exactly is going on from this imagery. But you can see the bottom line is basically that all of a sudden you have a vertically coherent vortex after about 30 seconds or so. But I wouldn't call this necessarily evidence of a descending vortex signature, despite this increase in rotation aloft there. So a couple other case studies that I looked at. This is sort of more preliminary work. I did this as a side project a few years ago, never really returned to it. So I'll sort of touch upon this a little bit loosely and a little bit quickly. But I looked at 4 other cases, 2 sort of more marginal tornado cases and 2 tornado failure cases that were taken from 2011 and 2012 here to look at the evolution of rotation associated with the marginal tornadoes, and then looking at times where you have intense rotation at low levels that never actually really materializes into a tornado for these failure cases. So doing a comparison in the rotation at roughly 300 meters above ground level for all of those 4 different cases, and I actually threw in, oh no, not for this one. So what I ended up finding was, particularly for this failure case, you never really have strong low-level rotation. Perhaps that's not really surprising. I mean, you might expect that you're missing low-level rotation in a tornado failure case. So the two failure cases are shown by this triangle here and this square here. So the triangles, you'll notice sort of, or I guess they're diamonds, they sort of stop here. We had, basically what I was doing was going through an intense, trying to identify a period of time where there's intense low-level rotation, and then all of a sudden it basically just deteriorates and totally goes away. That's why those diamonds stop there. And then with the other failure case, you never really achieve any kind of strong low-level rotation to begin with. Looking up a little bit higher at 600 meters, it paints a pretty similar story here. In general, the failure cases have weaker rotation than the success cases, even with the marginal. Now, here I added the El Reno case to show you a little bit of a difference between what we're seeing in these marginal cases versus a strong to violent tornado here. So the rotation associated with that was more intense pretty much across the board. And then looking at a higher height, roughly 1.2 kilometers or so above the ground. Now, here's where things start to get a little bit interesting, and there doesn't really appear to be a very clear trend. So this failure case has pretty strong rotation aloft, and it kind of alternates here. It weakens a little bit, but it's not really different a whole lot from the other kind of marginal cases that we see here. So what we end up sort of taking away from this is that aloft, there doesn't seem to be a very clear discrimination in the intensity of rotation between the failure cases and the genesis cases. So a couple quick and dirty preliminary conclusions. There was no evidence of a descending TVS for any case presented thus far based upon the rapid scan data. Also, tornado, in comparison with tornadogenesis versus failure cases, the failure cases tend to have weaker rotation at the lowest levels, which is really not surprising. There was pre-existing low-level vertical vorticity present in almost all of the cases with tornado formation. So there actually was pre-existing vorticity that was there already. So we're not really creating something from nothing based upon the cases that we are looking at here. And also, perhaps interestingly, there's not really a very clear discrimination in the strength of the rotation between these various different cases at heights greater than about 1 kilometer or so. So it appears that it's really the difference between these tornadic versus non-tornadic cases is really happening in these lowest levels. So we're talking less than 1 kilometer or so. So the question then becomes, what makes the difference? Is this an environmental thing where there's some, buoyancy or shear considerations? Is it storm related, where you can kind of have stronger convergence associated with rear flank downdraft or an internal momentum surge, or what's the case here? By the way, I'm not going to answer those questions. They're just kind of questions for musing at this point. So all this information is a good start, but there are some pretty significant limitations, and most notably is that none of these tornadogenesis cases have data that are very near the ground. So we're talking like less than 100 to 300 meters above ground level. I think the lowest was roughly 250 meters with one of the Mike French cases. So this sort of, the follow-up to this is then what is happening right at the ground and immediately above the ground as a tornado forms? And then how does this near ground rotation fit into the context of the overall evolution of the deeper layer rotation? So we're talking about, the tornado more along the lines of, hundreds of meters deep to perhaps, upwards of about 3 kilometers or so. And then another additional piece that's not being discussed is what's happening visually. So what are people actually seeing with their eyes? And how does this fit into the context of what we're observing in the radar data? So in 2013, 31 May, another violent tornado outside of El Reno. I say again, this is like three El Reno tornadoes that have happened now at this, in the context of about 7 years, I believe. So I was able to get a really great data set with the RACS pool, myself and Jeff Snyder and Howie. And this data set had 360-degree PPIs at 11 elevation angles over a time scale of about 25 seconds. And we were able to actually achieve data collection at a 0-degree elevation angle at a range of about 8 kilometers during tornadogenesis. And this was enabled by the fact that we were just kind of on a little rise. So we had very minimal ground clutter issues. If you take a look, this was the deployment location for that data set. And Anton Simon and others also put together a really extensive visual observational data set that they basically crowdsourced video and locations and photographs from as many chasers as they possibly could, and put this all together in kind of a self-contained online web interface that they refer to as the TED project. So these two kind of coupled together really provide the strong evidence that we've been looking for with regard to the tornado behavior, especially at low levels. So a little bit about the El Reno survey that they did. They had about 95 contributors who gave video and photograph information to their project, Anton's project. And for all of the videos, they synced the videos in time and geo-referenced the videos using stationary objects that were visible in the photography and the videography, and coupled that with locations that were known from Google Earth. And then they achieved temporal resolution and essentially synced all of these videos together with temporal accuracy of 0.03 of a second, so basically one video frame, by using lightning flash events. So they were able to cross-check lightning flash events in the camera timestamp, and they cross-checked that with National Lightning Detection Network and the lightning mapping array in Oklahoma to achieve this temporal syncing. So they talk about this a little bit more in their BAMS article that was published in 2016. I'm not going to belabor that very much more, but this is an example of what they were doing. So they have a radar image on the back, and they have the locations of all of these various different chasers here in these little blue triangles, and then you can click on the various different individuals and pull up their video from a particular time, and then you can work your way forward and backward and so forth. And one thing I wanted to draw your attention to was how much the perspective actually matters when you're looking at these tornadoes. So if you take a look, all of these timestamps, you can't really see the one in the upper left because I have that covered up, but all of these timestamps are from the exact same time down to, again, the 100th, I guess, millisecond here. So very, very high temporal resolution with these camera images here. And notice how so this particular image was taken roughly at this location, looking back at a tornado that was developing back here. This one was from this location, zoomed in a little bit more here, but looking at roughly the same image as what number one is looking at. And then you have these two other people down here. One of them is kind of on the southern end of the hook echo, and then the other's ahead of the hook echo, more in kind of the info notch area there. But in the bottom two images, you can't even tell that there's a tornado on the ground at this point in time. So it really makes an important difference as far as where you physically are located and what you're able to see. So really the initial sort of thought-provoking question that happened to me, I was reading Anton's BAMS article, and he was talking about tornadogenesis and showing images of a tornado at 2302. However, in Howie's article that he put together from 2014 that essentially presented a synoptic and mesoscale overview of the event, he attributed a coherent tornado signature through the radar data that began roughly around 23:03:45, so approximately a minute and 20 to a minute and 30 seconds after the visual of this condensation funnel. NWS start time is listed as 23:04. So what's going on here? This was kind of curious because we have a radar indicated tornadogenesis time closer to 23:04, which again is the time that you have a vertically coherent vortex. And then this picture where you have precise temporal reckoning with the image there. So I was very curious about this, and I started looking at the RAXPOL data at higher elevations, higher elevation angles here. And what I ended up finding was it didn't seem to add up until I looked at the 0 degree elevation angle data. So Oftentimes these data are kind of blown off. They can be a little bit contaminated by ground clutter. In this image here, you can see the actual grid system of the blocks and the streets in Oklahoma, where you have trees lining the streets, where you have phone poles, etc. And oftentimes the data are a little bit poor quality. They can be a little bit noisier, so I really wasn't looking at that. But once I did, it put things into perspective. So the series of images that I'm going to show here started at about 22:56. So this is roughly 7 minutes or so prior to the official tornadogenesis time. And what we can see here is the radar is located over here. We have a very clear, well-defined rear flank gust front over here. We have some low-level rotation that's kind of broad at the surface here. And aloft, we actually have a little bit of a couplet from an old brief tornado that had spun up and then decayed. So let's go through with time here and look at how things evolve. And the time steps, by the way, here are roughly every 30 seconds. So I'm actually manually clipping through this so I can kind of go back and forth here. So what becomes interesting is right about this time frame. So I'm going to back up and show you. So we go from having this sort of broad rotation here, which is associated with that old vortex. Here, by this point in time, that little signature that we saw at 2 degrees is gone. So we're looking kind of here initially. And then all of a sudden, right about this time, we notice that, oh, wait a second, there's something else going on a little bit off to the east, about 3 kilometers or so off to the east. And hey, if you look at the reflectivity here at the surface, you can really see this little hook thing starting to form. So we're actually getting a little bit of a velocity couplet going on here at the surface at 0 degrees, which is more or less about 10 meters or so above ground level. If we look aloft at 200 at the 2 degree elevation angle, which by the way is at an elevation of roughly 300 meters or so, you can see some broad circulation there, but there's definitely not like a tornado vortex signature element to this. Going forward here, now we definitely, okay, by this scan, this is 2302. This is a tornado signature right here. You have the couplet of strong inbounds adjacent to the couplet or adjacent to that area of strong outbounds. And notice the time, 23:02:17. If we go forward, or if we go up in elevation, again, we see evidence of broad cyclonic circulation, but you definitely do not have a couplet there. So what appears to be happening is something is happening right at the surface that's generating this vertical vorticity and essentially spinning up a tornado that's confined to a vertical depth below 300 meters, because we're not seeing that in our 2 degree elevation scan. So this, at this point in time, my mind starts to be blown, and I'm like, oh my gosh, like what is this? What is going on? So remember that those images that we saw of the funnel clouds were taken at 23:02:25. So we are confirming that when we're seeing this rotation in the radar, we actually have a visual of a funnel cloud. So going forward in time a little bit more, we can see that intensifies even more. By this time, 23:03, we have a very, what I would call a pretty strong vortex signature essentially at the ground. And this is really the first time now at about 2 degrees where we're seeing a little bit of evidence of what might be the developing or the development of a TVS. And then going forward, boom, by 23:03:47, now we definitely have sort of a vertically continuous vortex between the surface and 2 degree elevation angles. So, but if we go backward in time, this happens, the first, I would call this sort of the first sort of pre-tornadic vortex signature here. And this is occurring, roughly 2 minutes prior to that, this scan here, this 23:07, when we definitely are seeing, or 23:03:47, when we were definitely seeing a vertically coherent vortex there. So when I went through and actually identified what I was calling a tornado signature, what I basically found was that we had this sort of pre-tornadic couplet that appeared, like I showed you, relatively early on, and it intensified, it strengthened, and then it becomes roughly what I would consider a tornadic signature at this point, where it has a delta V value of greater than 40 meters per second. And then the visual of the condensation funnel is immediately after that, just within several seconds after that. And then so by the way, I should mention that I was looking at all elevation angles that we have and identifying tornado signatures in all of them, and there was no tornado signature above this 0-degree elevation angle in any of these until we get to this point here, which was the sort of official start time in the Bluestein manuscript of when tornadogenesis occurred. But we definitely see that it was present at the near surface heights, and then it almost sort of appears to have that bottom-up criteria where you see it now at this the next elevation angle, and then all of a sudden, boom, it's present essentially more or less through the entire depth of the column. Now notice that there are two elevation angles here that don't have a tornado signature in this particular scan. That actually has been seen before, and we suspect that that might have to do with a slight stable layer associated with the convective inhibition in the synoptic environment for that day, where you have a harder time actually generating a coherent vortex in those elevations there. But then by this time that has filled in, and you have basically a tornado signature all the way up from the surface to about 3.5 kilometers in depth. And by the way, we stopped, essentially our volume topped out here, so it doesn't mean that there's no tornado signature above this, it just means we didn't collect data that high up. So some interesting kind of comparisons looking at that El Reno tornado at various different elevation angles. We can see that, so now this is, by the way, I'm going to take a step back real quick and just mention, this is looking at the actual intensity of rotation at various different elevation angles. This does not mean that the tornado signature criteria have been met here. Oftentimes it's too broad to be considered an actual tornado signature, but I was still measuring the intensity of that rotation from the maximum inbound to the maximum out velocities there. So what we can see is initially we have stronger rotation aloft than we do at the surface, and then, but everywhere ubiquitously we're seeing sort of an increase in that rotation, and then all of a sudden at tornadogenesis time we have a sudden sort of flip-flop in this pattern here, where all of a sudden the low-level vortex starts to be stronger than what's happening aloft here, and I think that's kind of an interesting little musing there. If we look at the pattern at even higher elevation angles, so comparing it to 6 degrees up to 20 degrees, 20 degrees is roughly, again, about 3.5 kilometers. Again, prior to tornadogenesis, there's sort of a trend to have increasing rotation with height here, although it sort of inverts a little bit around this tornadogenesis time. But definitely around tornadogenesis, you see that 0-degree intensity is the strongest rotation out of the whole, out of the whole volume, and it actually is such that the rotation weakens as you go up with height there. So some conclusions from this El Reno data set. We have a visual condensation funnel about 1 minute and 20 seconds prior to this vertically coherent vortex that was identified by the radar. We also have this tornado signature that existed at the surface, so roughly about 10 meters or so above ground level, for about 1 minute and 30 seconds prior to, again, that vertically coherent vortex. And if you include that subtornadic vortex, that was present for about 3 minutes before the actual vertically coherent vortex. So we're essentially confirming the bottom-up process here, especially because we have that one scan where we have the tornado signature at both the lowest elevation angle and the next elevation angle up, and then all of a sudden you have this almost mutual contraction of the vorticity, and you have the formation of the tornado. And this process is occurring very rapidly, so we're talking about roughly 30 seconds or less. Another thing that was very eye-catching is that there was a considerable difference in the wind field between the 0-degree scan and the 2-degree scan. So over, essentially the surface versus 300 meters above ground. And then the TED data provided a really valuable confirmation of what is visually happening according to what the eye was seeing with respect to those funnel clouds. There was also a general trend of increasing rotation prior to tornadogenesis, but the tornadogenesis period marked this transition between the relationship of intensity of rotation and height. So prior to tornadogenesis, we had a scenario where rotation tended to increase with height, and then after tornadogenesis, the rotation tended to decrease with height. So a little bit of a flip-flop there. All right, so I'm going to put my little personal spin on this. This has not been peer-reviewed, so that's kind of the major caveat here. I haven't passed this through other than verbally with colleagues here. But I wanted to address what I think is happening here with this process with tornadogenesis here. So this is evidence-based, not specifically peer-reviewed. So what I think is going on is that, I guess let me back up a second. There's sort of a traditional explanation through like the Markowski-Richardson explanation where you have baroclinically generated vorticity along the forward flank of the supercell that gets advected around the backside of the supercell, encounters the RFD, gets tilted, and then gets advected downward to progressively lower levels. And then when you get this radial convergence into the updraft, it gets tilted even further, and you get kind of contraction of the vorticity and a stretching of it, and that forms a tornado. So what I always have a hard time sort of still explaining the rotation at the ground level, though, through that particular process. So that's just kind of my own thing. That's not, again, peer-reviewed. But what I think is probably happening here is that we do see this generation of horizontal vorticity along that forward flank downdraft gust front area that's generated by the buoyancy gradients between the rain-cooled air in the forward flank and then the warm moist air in the inflow regime. And the trajectories of the air are such that it wraps it around the backside of the mesocyclone. And then you get this vertical velocity gradient here that essentially tilts this vorticity up into the vertical. So here we have more or less our forward flank downdraft, our rear flank downdraft back here. These lines sort of outline border of precipitation with our forward flank here, our hook echo and rear flank area over there. We get the generation of this baroclinically induced horizontal vorticity, gets advected around the backside of the updraft, and it does get it might get advected downward initially, but it also appears to probably feed the low-level mesocyclone. So we're talking about on the order of 300 to 500 meters or so above ground level. So that baroclinically generated vorticity is helping to fuel a strong low-level mesocyclone that's going to be important here in the very near future. So moving on from that. Actually, I guess I'm not moving on from that yet. So what happens here is that baroclinically generated vorticity gets tilted into the vertical, and it induces a low pressure perturbation in this 300 to 500 meter above ground level kind of range here. So that low pressure is then going to induce an upward directed pressure gradient force, which is going to drive an updraft below this strengthening low-level mesocyclone. Then this is sort of where things get a little bit more sketchy. So I think that under certain conditions, you may actually get frictional shear that generates sufficient horizontal vorticity at low levels near the ground. And this frictional shear is associated with the shear of the rear flank downdraft air. So you have strong westerly wind just above the surface, frictional drag immediately at the surface that's reducing your velocity, which is creating a vorticity vector that's essentially directed to the north here under these circumstances. And then if you get this vorticity in the proper location, it will experience a convergence into that updraft that's associated with a low pressure perturbation that's generated again from that vertical vorticity that has been tilted from the forward flank. So if that, then essentially between that rear flank downdraft, that downward moving air that's now kind of wrapping around the south side of the updraft, you have essentially this source of rotation at extremely low levels. We're talking at the surface here, more or less, just above the surface, again, in the lowest 100 meters or so. As you have this gradient between the downdraft and the updraft here, that starts to get tilted, and that tilting then essentially can create vertical vorticity. And if you get that vertical vorticity in a correct location below that strengthening low-level mesocyclone, then you can essentially stretch it out, and over a very, very short period of time, when you have a combination of that stretching and the convergence occurring, you get a tornado to form relatively rapidly. And I think this also explains why we might get tornadogenesis in some cases and not other cases. With respect to the exact timing and placement of this frictionally induced shear when it's the largest, is it associated with an internal momentum surge? Are there specific land features perhaps that are increasing our frictional drag, that are therefore going to increase surface roughness and increase our shear as well. So it's kind of contingent on a lot of sort of smaller scale scenarios and features. So some general sort of takeaways and musings here is that tornadogenesis, I believe, is truly a very rapid process, but I think our eyes oftentimes deceive us with how rapid that process is. Sometimes we don't actually see evidence of a debris cloud on the ground, and we might just see a funnel cloud above, and as a result of that, you don't think that there's a tornado on the ground, but if you have a radar there, you're actually confirming that you have tornadic strength velocities very low to the ground. So I do think that there's a degree of deception that goes with the visual observations. Also, this process is happening so rapidly, and I'm sorry for you operational meteorologists who are having to make forecasts and issue tornado warnings based upon a process that increasingly is showing evidence of being very challenging to forecast and also occurring very rapidly. So, issuing forecasts with 100% certainty, I think, is probably ultimately unrealistic and unachievable. So the best thing that we can do is sort of do a, probabilistic type of outlook here for these individual storms. Also, it appears that small-scale processes, particularly on the microscale, probably friction, are very likely very important. And up to this point, I think they have been largely sort of underestimated and brushed aside, predominantly because they're very challenging and they're very complicated to resolve. So people who are doing numerical simulations and computer analysis oftentimes actually turn friction off in their models. So you can still generate a tornado that way, but it's ultimately not realistically representing what is actually happening in the real environment, in the real atmosphere. And again, our eyes are likely deceiving us. All right, so list of references there. I'm just going to back up and kind of go back to this takeaways and musings, and I will stop there. If anybody has any questions or comments or want to open discussion, I'm more than happy to start that process now.
All right, well, thank you, Jana. I guess since I've got the mic, I will ask the first question or comment here. Matter of fact, I had just attended a previous webinar this morning, Dr. Catherine Finley. She's also worked with Lee Orff quite a bit with sure the simulations you've seen, and a lot of what you talk about on the forward flank seems to match that streamwise vorticity current that feeds that the increased streamwise vorticity directly into intensifying the low level meso. The one thing that is obvious in some of their, I guess, simulations is, this cascade also of pre-existing vertical vorticity along the forward flank that feeds into the tornado, as well as a lot of the source region for the air that comes in the tornado actually comes from farther into the cold air of the forward flank region, and how that air is directly feeding in to that tornado and seems to be really important beyond even what may be going on with the rear flank. And so I'm just kind of curious to hear your thoughts on that, because it seems like we're getting a better consensus with this more or less streamwise vorticity current intensifying the low level meso, but yet, from an operational perspective, that still doesn't equal tornado, because we've got all these thermodynamic processes that can completely annihilate whatever the low level meso is trying to do. So curious to hear your thoughts on that.
Yeah, that's a really great point and a really great question. And my thoughts are, I don't have an answer for you explicitly, but I really think that all of these small little pieces are very important. And when you get into the context of the thermodynamics and how warm or how cool that that downdraft air actually is, we still even in the context of friction, I'm not attributing friction, like the actual source of the air, being necessarily within the RFD. I don't know where that air is ultimately coming from. So it could perhaps be coming from that colder air in the forward flank that is, enters into the RFD area there and can contribute to that perhaps, and perhaps not. I mean, perhaps there's something entirely different going on there. But I think really the sort of ultimate takeaway that I have is that it's really complicated and there's so much going on. And I think additionally, it's not all the same thing in every case. I think it's very situational scenario where what works in one case might not necessarily work in another case, and where the air comes from in one case might not necessarily be where the air comes from in another case. And you might have multiple different modes of tornadogenesis that's actually occurring in these various different scenarios there. So I don't know that I really answered your question, but that's sort of my best attempt to kind of address that.
No, that was perfect. If anything, I think we're finding out, especially in weather service, is that, this thought process that we could just look for couplets is really a fool's gold situation, because these processes are occurring almost simultaneously, and the background noise you see with a non-tornadic versus a tornadic case when it comes to just looking at, say, the meso at a kilometer is not going to help you, because these processes are occurring, first of all, so low that the ADD is going to overshoot it, and two, due to the temporal limitations, even if we could, we're probably going to skip past it. And so, it's obviously a process where just looking for couplets is not going to advance the science and our ability to issue warnings. So very good.
Yeah.
So with that, if you guys have or gals have any questions, just raise your hand within the GoTo applet there, or you can also type your questions in, and I can repeat those. So go ahead for anybody that would like to ask any questions. Okay, I do have one here. Jeremy, I will go ahead and unmute you.
Thanks, Aaron. I just wanted to say thanks for doing the talk. I hated to leave you here with awkward silence at the end. So thank you so much for presenting this to us, and very interesting stuff. I'm still trying to wrap my head around all of it. That's all I wanted to say. I just didn't want to leave you with awkward silence at the end of your talk.
Well, I appreciate it. Thank you for that feedback.
Okay, well, I don't see any others. First of all, thanks once again, Jana, for being willing to participate in our R2 series. We really trying to get just that connection back with the research community such as you into operations. I wish we could do it more, but we're doing the best we can. And also just appreciate everybody's time to join in, and hopefully you learned. And if you have any other questions that come up after this, feel free to ship them to me or to Jana or whoever, and we'll get them directed and try to do the best we can to get those answered. Otherwise, if that's it, I guess we're done, and thank you very much for joining today.
All right, yeah, thanks. I just want to end saying, I'm available through email or for any other method that you can think of. So I'm happy to field emails or questions that way as well, if you think of something after the fact or whatever the case may be. So thanks everybody very much for attending.